Thank you. So today I'm going to talk about improving runtime scaling for synthesis in place and route for very large designs. I'm going to first point out how crappy the runtime still is, and then I'll go into standard techniques that are already used in industry to speed things up and discuss what further can be done, and then I'll give an example with scan chain wire length minimization. So people ask me, why are your tools so damn slow? Why don't you speed them up with GPU acceleration? This is easy, come on, it should have been solved yesterday. Why haven't you done it? And it's not that easy. But in that context, if you look at single-threaded spec-int performance, it's sped up by an order of magnitude. But then on top of that, we have about 100x in terms of the number of cores available. And we're only seeing on the order of maybe a 10x speed up in synthesis in place and route in the past 20 years. So this is a problem. And we'd love to be able to run a design through this kind of flow in a day, if it's 1 million gates. So we're not even hitting that. And very large designs, 5 million gates, can take more than a week, 2 weeks. So the basic problem is that a lot of the algorithms that you have are not highly parallelizable. So there are a few exceptions to this, and you may, for example, see static timing analysis with lots of corners being able to use 40 threads. But if you look at a typical commercial tool, your average thread utilization through the flow may be only 10 threads. There are various reasons for this. You need to synchronize, you need mutual exclusion locks to avoid read-write conflicts. You have overheads such as file I/O, cache misses, and so forth. And if you tell me, hey, go and use GPU acceleration, we have these brilliant academic results, yes, that is true, but then these are not commercial quality. And if you go and tell your customers, oh, by the way, the results are 5% worse, well, then they'll switch from ICC2 to a Novus, and then you have a problem. So we have to maintain quality. Speeding up just one engine in the flow is not enough. The flow has hundreds of different engines, and we're struggle to get a good speed up as we make improvements because of Amdahl's law. So let's take an example. Let's take global placement. Global placement may take on the order of 10% of runtime in pre-CTS, in the flow before clock tree synthesis. And then let's say we can speed up 90% of that global placement runtime by a factor of 10 because it's already quite multi-threaded. Well, if we do that, we get 11% speed up at best in pre-CTS by speeding up the global placement. I think that number's actually a little off, but anyway. I think that number should be 9%. Or it's 11% speed up. It depends whether you do one or the other. Anyway, but the actual flow speed up is only 3%. So you have to speed up a lot of the engines in the flow to actually see a good speed up overall. Standard techniques that are used within commercial synthesis in place and route software. So multi-threading, multi-process, and then distributed computing. Distributed computing is more used in sign-off. So multi-threading is faster. If you have legacy code like we had with Nitro, you hit a lot of bugs and crashes, and it's a real pain to get it working well. And so a typical approach in multi-threading, as an example, there are different approaches, is to do parallel optimization of small windows of logic. And the threads will have separate copies of some of the data to avoid contention and to avoid the overhead for mutexes accessing that data. You want your regions ideally to be spatially separate to avoid contention for utilization, routing resources, and so forth. And you will also have connected timing paths ideally in the same region together to optimize them better. And you also need to constrain boundary crossings, so if you're doing optimization on one side and optimization on the other side, that they don't conflict. And then when you combine your results back together, you may need to either reject some of the changes, unroll them, or to quickly fix them. So for example, doing a fast timing optimization after you've done multi-threaded area optimization. So taking a look beyond what is done today in commercial software, what can we do? Well, there's a fundamental problem with the way flows work today. They're a monolithic sequence of flow steps. I'm going to do global placement. Now I'm going to do high fan-out synthesis, global routing, buffering, and so forth, gate sizing, and I will do like timing optimization and then area optimization and so forth, but each of these are typically discrete steps. You don't do area optimization in parallel with timing optimization, in setup timing optimization. Why not? I think you can. And I say this because for setup timing optimization, that is where you're, critical paths, you don't have slack. For area or hold optimization, you have plenty of slack. You should be able to do optimization of that in parallel. Depends if you're in a situation where your thread utilization is low and you have enough memory bandwidth. In that case, you can run it on the same server. Otherwise, you have the overhead of running stuff distributed. You can also, of course, do multi-objective optimization. I don't see enough of that done in synthesis and place and route today. But beyond that, that will not get you that much speed up. So what do we really need in the big picture? If you look at how industrial designs are done today, I have, a 200 billion chip from, transistor chip from NVIDIA. A lot of that is replicated logic, but still they would love to, take these large blocks and run them through. So they split them up into small things. Some of them are replicated, the larger parts in different pieces. And they run all of those, but it's a very manual process. So imagine that you come up in academia, because there's it's a problem that's not well solved and it's something that we could get research help with from academia. Imagine that you figure out a way to automatically split this up. You can use min-cut. There's other smarter approaches too, and you need to keep critical timing paths together. And you do a bunch of optimization in parallel, and then you can recombine it back together and then do some further splitting and then further re-optimize or do top-level chiplet stuff. But that is a good problem to better automate to speed things up so you can do lots of things in parallel. You take a 10 million gate chip, split it into 100 different pieces, run those pieces in parallel, you have a queue, and you're going to have to accept some loss of quality of results, but maybe you can mitigate that by partitioning and doing some further optimization. So I'm going to give you a simple example of some coding that I did, where for scan chain wire length minimization, we have a large scan partition. We can split that up to improve the parallelization. So scan chain wire length minimization is essentially a multi-depot, multiple traveling salesman NP-hard problem. The objective is to minimize the wire length. We need to avoid violating the maximum bit counts on each chain, and we ideally want to balance bit counts across chains in the partition. And there's a scan-def format that specifies the maximum number of bits for each chain. And we can, within chains, we can do the classic traveling salesman optimization, where you simply minimize the length around that path. Or you can also swap between different chains in the same scan partition. So the simple algorithm I took was, I thought, hey, I've got 2 million flip-flops in this design. Why don't I just say, hey, these ones which are initially, for some random reason, got placed here and connected together in some initial scan chains from synthesis, I am going to say, I'm going to partition these up in some manner and allow you to optimize within these little sub-partitions, and I'm going to accept some suboptimality. So we split first vertically and then horizontally, and we're using just simply the average position in a scan chain, and by sub-partitioning in this manner, you won't be able to swap with all the other scan chains, but you can swap with enough of them that you still fairly good results. So these are the benchmark details here. Let me see if I can move this out of the way so it's easy to see. There you go. Okay. There you go. That's better. So these benchmarks are large industrial benchmarks. So the largest standard cell count in these designs is up to 11 million gates. The number of flip-flops is up to 2 million. They have very large number of scan chains, up to 30,000. And the big scan partitions have a lot of scan chains. And we can split these up. And the largest number of splits we get to down to below 100,000 bits in each sub-partition is 32 splits. Or 32 total subsections. So this is I'm going to discuss the impact on runtime of the splitting. But I want to give the context that doing parallelization is not the only way to solve this problem. So we had the problem that we had several test cases that were just damn slow. And they're damn slow because they're over-constrained. You can't meet the max bit constraint. There's no way you can balance them. So I came up with this quick and dirty hack, the algorithm that I showed you, and say, damn these constraints which we're going to violate. I don't care. Just go ahead and do reordering swapping within these little subpartitions, and that'll give a certain speed up. So comparing on those initial results, we get up to about a 4x speed up by splitting. Because once we split into subpartitions, we can run each of those subpartitions for scan in parallel. The big scan partition you can't do in parallel, but once you subpartition, you can. Now, once another developer had fixed the runtime issue that we had with the max bit constraints, the speed up by splitting goes down to a factor of 3.2 geometric mean. And then I spent another 2 months or so of actual hard work and went and refactored the code to fix how we were comparing scan nodes, to avoid caching issues, which were actually burning a lot of runtime, to speed up checking the hierarchy. And that gave us a significant speed up as well. And then after that, actually splitting the scan partitions only gives us less than a factor of 2 speed up. So the point I'm trying to make is sometimes the hard work in terms of software development is not just coming up with a quick and dirty algorithm that makes everything parallel. You can actually get better results, but take the extra time to engineer the software better. In terms of the actual multi-threading utilization, having done this kind of splitting, at best, and I was surprised at how low these values were, at best with splitting, the thread utilization is only about 4.4 threads. Without splitting, it's even lower because these big partitions are what limit you in terms of runtime. And the other thing you see, it's kind of an Amdahl's law consequence, is as you're doing splitting into subpartitions to run them all in parallel, it turns out your overheads are what dominate, and you have to go and speed up those overheads to actually speed things up. So that was the point I made earlier in the general kind of sense that not only do I have to speed up my little core engines, but I have to speed up everything else, all my overheads. So it's actually very hard to speed up synthesis and place and route as a whole. So I did these approximations by, suboptimality by splitting up my scan partitions. What is the actual impact on the wire length? Well, the initial results were quite bad on some designs, so ignore those for a sec. Across the other results, the worst impact on wire length is up to 10% higher, and the average is 2% higher. So it's not that high a cost. Is this acceptable? No, it's not there in commercial flow today because 2% higher is unacceptable. But I personally think that you need to make some of those sacrifices. And you could certainly rerun the partitioning, and you do like maybe 6 calls of scan chain reordering within the flow in pre-CTS, for example. So you can probably mitigate that overhead too. So in conclusion, back at the high level, speeding up synthesis and place and route takes many fixes across many engines. And we have long runtime poles, which limit our multi-threading utilization and impact the total runtime. It's difficult for much of the code to achieve high parallelism. And what we should do is look beyond the traditional monolithic flows today, do multi-objective optimization, run different objectives in parallel on portions of the design which don't kind of impact each other too much, and also split up large designs, and that's the open research problem which I throw out to the academic community. How do we do this smarter in an automatic fashion? And then on the scan chain reordering and so forth, we got a lot of speed up simply by bailing out early and being smarter about dealing with difficult or max bit constraints that couldn't be met. Refactoring also gave us a big speed up. And then splitting the large scan partition, it gave us a factor of 3.5x, but that was only 1.8x after the other fixes, at the cost of 2% higher wire length. And the development time for all the kind of good, smart coding that didn't degrade results was 2.5 worker months versus 2 weeks for the quick and dirty algorithm, which, it was a good hack. Thread utilization remained 4. The refactoring that we did not just sped up these big designs by a significant factor, it also gave us a 25% reduction on typical designs. So fix your bad runtimes. It'll help you more broadly, but you have a lot of work to do to actually get these improvements across the full flow. Thank you.
Thank you, David. Hello? Questions?
It seems like what the top-level user who's breaking this down into 100 pieces to be done in parallel would like to know is what's the derivative of runtime with respect to design changes?
Right.
In other words, if this one is bad, how much percentage of area do I need to give up to make this fast?
Yeah.
Is there any way to get that information?
So, I mean, for the examples which I showed for scan, if we split it up into 32 different partitions, the overhead was an average of 2% Y length. Have we done this more broadly and have we got those results more broadly? No. But yeah, I mean, that's the exact trade-off. And the point is that by splitting it up into, by a factor of n split, you don't get a factor of n speed up. You might get a factor of 2 or 3 or 4, but it's not that good a speed up. And you still got to use a lot of compute to get there. And yeah, there will be some trade-offs. I suspect your actual trade-offs, if you do this smart and you kind of repartition and re-optimize again later, your overheads are probably somewhere in the range of 10 or 20% maybe. For Y length, and there'll be some impact on quality results, and then it depends how hard it is to meet timing, and depending on how hard it is to meet timing, that'll impact your power, the banana curve. So it's hard to give quantifiable numbers. It'll be design dependent.
Yeah, I'm curious for the scan chain optimization or vehicle routing problem. Did you compare to state-of-the-art solvers? So there are now also some that...
So no, we did not compare to state-of-the-art.
Okay.
I will say that we do have embedded down in the code some standard, traveling salesman solution. But we have not compared to multi-depot, multi-traveling salesman state-of-the-art, and I think that would be interesting.
Okay.
So thank you, David. Oh, sorry.
Yeah, that's fine, I see you.
Yeah. So coincidentally, David over here with a lab mate pushed a rebooted scan chain solver into our ABK group repo, and we had previously gotten some desired functionality inputs from folks like Philippe Sauter and others at ETH and folks at Google. And do you have a spec for what you really want? Because we hear about multi-bit flops and scan groups.
I can discuss it with you. I don't have a clear spec that I can share. I haven't got one written down, but I'm sure I could come up with one.
And would you be...
I'd be more than happy to guide some folks in the academic community on how you should do this.
And test cases? Or
cases?
synthetic realistic test cases?
That's a harder problem because most of the test cases we have are industrial, and I cannot share.
That's why I said synthetic realistic.
Yeah, but I mean, so can you come up with some synthetic test cases? Yes, but that's more work. So on my schedule, perhaps not. But I mean, I think probably some of the existing test cases you have may be adequate. Or we can talk.
I had a quick question. So when you're slicing things up, are you looking at the aspect ratio of the blocks as you slice, or just cutting?
It's brute force, stupid, just split. But I mean, so if you look at the example, right?
Yeah, that's I was looking at that.
So not all of them have the same aspect ratio by any means. And is this going to be suboptimal? Yeah, it'll be a little suboptimal, but it actually turns out to work okay. Because you've got so many chains with so many flip-flops across the design that you can do most of the optimization you need. And if you're smart, you go and repartition later and then you do another round and you'll get better results.
Okay, yeah, the aspect ratios are...
Yeah.
Okay.
They're not good aspect ratios in that sense.
Let's get one last question because we're already late.
So I wanted to ask a question about the GPU acceleration of synthesis, place, and route. Currently, the best known algorithm for placement is Andrews Group's conjugate gradient placement. So the GPU acceleration, you mentioned a paper.
Yeah, there's a C3PO ASP-DAC paper.
Is that sort of the current, in your opinion, the best GPU acceleration of placement?
So if you want my frank opinion, they haven't run on large designs. I don't think they compared versus the Innovus macro placer. They just compared versus the Innovus global placement. So I don't think their evaluation is adequate necessarily. It does look interesting. It's built on top of DreamPlace. They were using timing-driven and differentiable, routing the Rudy models and so forth. I think it's a good approach. Is it going to be commercial quality? I don't think necessarily. But I think we're getting closer and closer to academic results, being able to be competitive versus commercial. So I am personally going to help evaluate and compare. I don't have those results yet.
Thank you very much, David.
Thank you.